Okay, last time we have we observe this curve. Okay. The top one is just our functions. Okay. The bottom one is our estimations on how the first derivative looks like. Okay. The f prime, and how we are going to determine the functions become the f prime or derivative is based on the slope. Okay. So the slope, you see that the slope at the beginning is getting decreasing and then getting 0 and then increasing and 0 and then decreasing. Okay. And then we can convert them into the first derivative, and we can at least draw or sketch roughly how it looks like. However, we still may need some exact value on some points that you will learn later on chapter 4, which is how we apply derivative to sketch the curve. Right? So this is just reviewing the last part, and we have now some introductions on differentiable. Okay? We are left with these words or definitions that is about how the function can be differentiable. Okay? So the differentiable functions, what it means. Okay? But I think it's best to look on an example on how we can apply these words or these definitions into applications. Okay. Okay, maybe let me start with the, okay, for example, if we have functions that is the absolute value of x. Okay. The question is the function differentiable? Okay, that's the question. Okay, I will show you how we are going to prove whether this can be differentiated or not through some equations and proof with some numbers. But later I will show you how we can distinguish this case from the graph. Okay? And I think it will be easier with the graph. But let me show you if the functions, for example, if we start looking at the function itself, we know that we will have at least two conditions, right? Whether when the x is positive and when x is negative, right? So when x is positive, we will have the functions will be just x, right? When x is negative, we will have the functions is negative x, right? Okay, now we can set up. So if x is positive, okay, then the absolute value of x is x, and then we can choose that some h, that x plus h still positive. Okay. Now we have, by our definitions from the last part of our lectures, we have f prime is limit as h approach 0, okay, and this will result in x plus h, this is the functions, minus x over h. This is using the basis from the limit. Okay. This we are applying for. So at x positive, the x plus h become just positive, right? So we can write at x positive, we can write no problem, right? And then we can see that we can cancel this, and we know that for sure from this result it will be equal to 1, right? So f is differentiable for x is from x that is positive. Okay. So let me write, this is the first section. Okay, we can look another section, which is when x is negative. Okay? When x is negative. So if x is negative, the functions become negative x, right? Then similarly, from what we have done, we can write the derivative using the limit. Let me write the whole thing first. And this becomes, the absolute value becomes negative x plus h, negative x. And then over h. And now we can see clearly, if you look here, this is negative x, negative h, right? This is plus x. So we can cancel x, and we are left with negative h, right? So negative h divided by h is negative 1. Because we have the value, we can also say f is differentiable for x less than 0. Now the problem arises because this having two distinct values, we need to evaluate at x equals 0. Okay. So this is the second section. Now the third section, we need to compute for x equals 0. So we need to investigate f prime 0 equal f0 plus h minus f0 divided by h. And this results in, oh sorry, I forgot to write the limit. And it's resulting with the value of, absolute value of h divided by h. And we're still not sure whether it exists or not. Yeah. So we can write here if exists. Okay. Okay. Now how do we know that this is exists or not? What can we do? Any idea? Okay, this is if this is exists, but how do we know that this exists? What can we do? Any idea? And any follow-up method? Any idea? Put 0. Okay, but we still not clear if we put 0 whether it's okay or not. Remember, if you have limit approaching to some point, which method you need to have? Yes. So what you mean is we need to check the left hand limit and the right hand limit. Okay. So compute left and right hand limit. So limit approaching 0 from the right. Okay. We can write this in terms of h over h. From the right is the positive 1, of course, right? And this will be 1. And limit as h approaches 0 from the left, which is the less than 0 or the negative 1. And thus this becomes negative h over h, which resulting is negative 1. So, since this is different, what is our conclusion? Yes, limit not exist. Okay? Limit not exist. So since limits are different, limit not exist, and more importantly, the f prime 0 does not exist also. Then the conclusions are that the functions differentiable at all x except at x equals 0. So we can also write in terms like f prime x. This will be 1 and negative 1. This is if x is positive. This is if x is negative. Let me move a little bit to the right so I can make a picture in here. Maybe later, maybe the next page. Maybe just drawing the absolute value x. Okay, at least it seems this is the absolute value of x. Okay. Okay, from the graph absolute value of x, if we look closely, from what we have done in calculation and we have seen in the graph, the way that we can distinct or we can know immediately is, if you see any of this sharp notch here. Okay. Imagine you are walking from the left and walking from the right. If you have like sharp point, when you zoom in about this sharp point, can you define anything here? Will it be the same if we go from the left, if we go from the right? Especially if we know that this is just x. If we differentiate, like for example, this is increasing, right? Or if we see here, this is decreasing, this is increasing, right? So what about this point in the middle? Is it increasing or decreasing? We are not sure. We are not sure. It's not decrease or increase either. That's why it's not differentiable. And that's why if we try to make the graph of the derivative if we take this and make the derivative, so if we take this, according to the answer, it should be 1 and -1. So maybe let me draw, but it should be having discontinuity here. And this will be the f prime x. So we cannot define anything at x equals 0. So whenever you find any sharp point on your graph, it means that at that exact point you cannot differentiate. Okay? You cannot have any slope here. I think this absolute value of x is describing the important thing on differentiability. We move on here, you know the slope is -1. When you move here, the slope is +1. So in the middle here, we cannot define anything. Okay, so we left with the discontinuity at x equals 0. Okay. Okay. Okay, any questions first? Any question first? Okay. Okay. I hope this method can help you to at least process on how we can find or which interval that is differentiable or not. Okay. Okay, now we move to another theorem. Okay. So let me write two points and let me ask the question: if f is continuous, then f. Do not write first. Okay, I just want to check first. So we have two statements, statement A and statement B. Okay. Based on your understanding from previous slides, we have statement A, if functions continuous, then function is differentiable at A. So if function continues at A, then function is differentiable at A. The second statement, statement B, if function is differentiable at A, then f is continuous at A. Which one is the correct one? Who's A? Okay. Who's B? Actually, why B?
Just sounds good.
Okay, but it's good guess. It's good guess. Okay. If I take the graph back again, the absolute value. Okay. Is this a continuous function? The absolute value? Right? Absolute value. It's a continuous function, right? Because we can remember, whenever you draw any continuous functions, like when you draw on your paper with a pencil or pen, if it's continuous, you just draw and you never take away your pen, right? We can also draw the absolute value, right? Easily, without taking away your pen or pencil. So we say this is continuous, but it's not differentiable at x equals 0. Okay? So the first statement is not always true. It's not always true. So this is not always true. So let me write here. Okay. But the second statement, if you know that it's differentiable, it should be continuous. Okay? Get it? Get the logic? Okay? Now from this statement, let me just go to some drawing here. Okay. So whenever you find a corner like this one, the absolute value, like a sharp point, discontinuity, and you find the vertical tangent. If you find this tree, means that at this point here, at the middle here, you cannot differentiate. So it's not differentiable. So this means that how function fail to be differentiable. This happens because different value, right? The slope value different here, and we are not sure how much. And this is not continuous. And this is having the limit is infinity, right? Vertical. We're just adding some points here that this is infinity. Okay, now that's the last section actually on chapter 2. So chapter 2 has several sections up until 2.8. So this is 2.8. We learned the derivative as functions, and we know how the function can be differentiable or can be differentiated or not. And then we also learn how to sketch or to predict what will be or what the graph will be if we draw the first derivative from the function. Okay. And you can do that, like for example, you have a function and maybe you predict, oh, this looks like the first derivative, and you predict how the slope, positive, negative, right? And you can always derive and maybe having more and more graph. Okay? And probably in your exercise, hopefully I can send you exercise just to make sure you understand. Or I think your TA also will give you some homeworks maybe later, and to check the chapter 2, okay, the chapter 2 overview. Okay. Now we move to chapter 3. Okay, I hope you don't mind. We move to chapter 3. So chapter 3. So chapter 3 will be about the derivatives or the techniques or rules. Okay, we say this is differentiation rule. Okay. To begin, we can start with the functions that is a constant. Okay. So let C is a constant. So let C be a constant. And of course, if you are trying to look from the basis of our derivative, which is using limit, this is resulting in 0. Right? So we can write that if we have a constant, this is 0. So now you have a reason why if you have a constant like 8, 5, like line x equal 5 or x equal 2, what's the derivative of that? You can say it's 0. Why? You can explain, okay, because when we're using limit, it's getting 0. Not because you memorize, you derive the constant is 0. We know the reason. We know the reason. And then if we have f of x, maybe we start from 1. Or maybe we start from x. Okay. So y equal x or y equal x. So we start from a line that has slope 1, right? So this is y equal x, and the slope is equal 1, right? Or we can say the slope is our derivative of the functions, as we might see. So since this is 1, okay, and you can also clarify using the limit if you would like, if you want. You will get directly 1, right? So this will cancel, and h over h is just 1. Okay. And then the same way, we take maybe x with power of 2, we take x with power of 3. So when we take x squared, when you derive, this will be turns out to be 2x using the same limit equations. Okay. And then when you have, for example, of x with power of 4, the same way we'll get for x cubed. And now we are looking at a pattern. We are looking at a pattern. So by looking at x with power of 1, x with power of 2, x with power of 4, or x with power of n, we can develop a pattern from that formula. And it's based on what we have learned in the limit here. Okay? So if you maybe asked by like your junior or maybe someone younger than you, and why we can derive this, then the answer is we go back to the limit. This is the true definition for the derivative. Okay? So we can develop what we call the power rule. This is if n is a positive integer. There is some proof of this power rule, but I think I will just let the proof later on. I will just give it to you. But I think I will just go to just erase this because it's make some confusions. Because actually it can be any real number, and can be any real number. Because your textbook, it starts from giving you some examples and using the integer, and then they are using the other exponent, and then get the conclusion that n is any real number. So I don't know why they are using the integer at first. Okay, I think if you can just skip and then say that this is going to be for all real number. Okay, so if we have questions like find equations of tangent line and normal line, I just want to check your understanding on tangent and normal line to the curve y equal x squared of x at the point 1, 1. So two questions, finding the tangent line and finding the normal line. Okay, just checking with you. Okay, so if we have f of x or y equal x squared of x, we can write this x and then x with power of half, right? And we can write this as x 3/2. Okay, so our first derivative will be 3/2 x, and then this will be 3/2 minus 1, right? Or we can say this is 3/2 x with power of half or 3 over 2 square root of x. Okay. Now remember, every tangent problems you have, the idea is they always asking the slope. If they are asking the tangent line, they are asking the slope of the curve. So the curve is x square root of x, which means x with power of 3 over 2. And how to find slope is basically the first derivative. I think we have that last week. So this is the slope, but then they are giving you information that this is the point. So basically, this is the point that you are going to evaluate to find those slopes. Okay? So the slope at 1, then the slope at 1 is 3 over 2. Okay. Now the equation of tangent line will be y minus 1, and this is 3 over 2, x minus 1. Okay. And you can solve that. However, what is normal line? What is normal line?
Vertical to tangent line.
Yeah, vertical to tangent line. Okay. If you heard any normal in the, I think in physics or like in factors, that means the one that is going out of the plane, if you remember factors or in physics, right? So if we have a tangent line, probably if the tangent line here, let me draw. If I write this is the tangent line, then this will be the normal. So the normal line, or if we write this is, let's say it's n and tangent is m, then m multiplied by n will be -1. Or in our case here, our normal line will be -2 over 3. That means the normal line will be, this is not normal line, this is slope of normal line. Okay, so y minus 1 equal, and then x minus 1. Okay. Okay, that's just a quick example. Another rules that we will have is if you have a constant and a functions, and we derive all of it, then we can factorize the constant, and we just derive the function itself. So if C is a constant and F is differentiable function, and how to prove is basically the same. Okay, using the limit, okay, and as x or as h approaching 0, using the h, we can change this to another function g is equal c multiplied by f, and then we can use the limit, and you will see from the equation of limit you can factorize the c, and this is the result. Okay, any question first? Okay, I think so far it's still not really that difficult technique. Okay. Okay, let me go through. Another one is if you have sum and subtraction or difference. So if you have f of x plus g of x, this will be results in, or you can separate and differentiate each one. So this will be true also for the subtraction. So if you add or you subtract, it's the same thing. You can separate the equations. Okay, become two equations. Okay. If there's no question, so we can move to the next one. The next one is the exponential. Okay, so we know the terms exponential. So if someone says it's increased exponentially, it means that it's increased in a really fast increasing. Okay, let's write some functions that is b with power of x. Okay. So by using the definition for derivative, let me write the original equations so that you will always know that how you can write the equations. Okay, so write this equation, and then let's using the b with power of x. So this will be b with power of x plus h minus b with power of x, and then divide by h. Okay. Remember that b with power of x plus h we can write as b with power of x and b with power of h, right? So we can factorize b with power of x, and then write b with power of h minus 1 divided by h. Or even we can factorize b with power of x outside of limit, right? Because limit is using h to approach, so we can factorize b outside here. Okay. So we can get the b with power of x and the limit as h getting 0, b power of h minus 1 divided by h. Now, how to solve this? To solve this, we may need some additional constant. But if you look the limit form, if we are using x equals 0, here, it will be the same thing, right? So I can write in the explanation here that if we are evaluating at x equals 0, then this will be b with power of h minus 1 divided with h. Okay, so I can write these equations here, b with power of x, and then multiply with f prime 0. So at least we get this relations. Okay, do you want to continue or have a break?
Continue.
Continue, okay, so we can get out fast. So from here, this means that the rate of change of any exponential function is proportional to function itself. So what does it mean? What does the word mean? It means that if you differentiate any exponent, for example, b to the power of x, the result should have those terms. Okay? And remember, maybe some of you still remember, if you have e to the power of x, you derive, it's still e power of x, right? E power of x. So that means that every exponential, if you derive, the original form of those functions will arrive. Will appear. Okay. Now to solve this, okay, to know how do we connect this with the e that we know, we can start with some table values of b, okay, of number b. Okay, so let me write around here. So let b equal to, okay, and then let using some h. Okay, so for example, let me write h and then 2 with power of h minus 1 divided by h. Okay, this is just to predict or to estimate the value of the limit. Okay. So we want to know what is the value of this limit. So we are going to check with some number b. So first we check with b equal 2. And then b equal 3. So if you check with calculator, start maybe h is from 0.1. This start from 0.7177. This is 1.1612. And if you increase the decimals, okay. So if you make it shorter, okay. Now if you take it more and more, probably until 0.00001, this will turns out to be 0.69315. This is 1.09862. Okay, now from these conclusions, okay, at least we get the idea. If b equal 2, then the f prime 0 will be equal or approaching 0.693, and when b equal 3, we will have f prime 0 equal 1.099. So between b and 3, there exists the result that is equal 1. Okay. So between this, it should be having some result that equal 1, right? That is when b is equal with 2.7 something, right? And that is actually our definition of E from this point of view. We can have another definition of E, but I think that will be on a later date. But at least from here, we get some idea of how we get a number that resolving the f prime 0 to be 1. And that number we call E. So E is the number such that limit as h goes to 0, e with power of h minus 1 divided with h is equal 1. And as an implications, if we take the derivative of E, this will result E itself. And usually this is we called the natural exponent. Or natural exponent function. And E, why we call it natural exponent? Because E can be made into our nature, or our nature can have some patterns that when we extract those patterns, especially if it is related to any exponential statistics, it will always going to be with E. Okay? So it's going to be, so if we approach those numbers or those data set, they will all having some E inside those formula. And that's the intro 3.1. Okay, 3.1. Okay, the next sections we'll go through product rule and quotient rule. So let me write the general rule for the product rule, and then maybe having some proof. Okay, this is the general rule. Okay, so if we want to prove this, we can try to write another functions that is describing the f and g, like that. So I will use the capital F. Okay, and by using the definitions of a derivative, we can take the limit and then write down the formulations. And then we exchange to the f and g, all the terms. Okay. Now what's the deal with this, and how do we solve this? How do we take this limit and we need to simplify this limit? The idea is, if you see this is having f, g, right? But it's different. X plus h, this is x plus h is just x. So what I would like to do, or you would like to do, is remember that we have this, and this will be our definition of this f prime, right? Can we force, or can we manipulate this form to be having the same description as this one? Okay? And then we can have some certain f and g in groups. That's what we are doing. So this is a little bit tricky. Okay, this is a little bit tricky, but to solve this, we need to add and subtract. This form. Okay. So we can write this. And let me add and subtract in the middle. So plus okay. Now by doing so, we can group each one. Okay. Group each one, going to the x plus h and the other one. So first we can group. So grouping fx plus h and gx. Okay. So grouping. So this will be gx plus h. And then minus gx, right? And then we divide by h. And then plus limit as h going to be 0 of gx. This will be from fx plus h minus f of x. Okay, and we can see clearly, okay, these terms will be g prime f x. This is just f of x. This is g of x, and this is f prime x, which are getting the statement of product rule that we write at the beginning. So we can write that this is resulting f of x, g prime of x plus g of x, and then f prime x. Or we can write, usually I write f prime x g to help you remember how it looks like. And then this becomes our product rule. So d dx, and this is f of x, and then g of x. Usually I'm always write f prime g, g prime f, because usually I will relate this formula to the quotient rule, just to help you easily apply the formula. But anyway, if you write f g prime, g prime is the same. And that's the product rule. So at least today I would like to have a product rule and a quotient rule. And if we have time, maybe at the end, just an intro to the chain rule. Okay. So I would like to just to keep all the techniques at the very beginning, and then later on we can practice, and we will see which one is still not clear, or we need to have some review. Okay, so this is the product rule. Okay, another one is the quotient rule. So this will be the formula f of x divided by g of x. And usually when you write in terms of, this will have squared at the bottom. Then you write f prime x, g of x minus g prime x, f of x. Okay. To set up the rule, similar with the product rule, we can set up, maybe let the big F like this, and this become our f of x divided by g of x. And then set up our definition using limit, okay, using limit. So we can have, this will be f x plus h and g x plus h minus So let's exchange all the functions. Okay, now let's simplify our equations. So write down so let's move down here. And then this will be g of x, f x plus h, and minus f of x, and then g x plus h. Okay. Now, similar with the previous, okay, similar with the product rule, what we are going to do is we are taking, or we need to add something here and maybe minus something, so that we will have, or we can group each one another, that we can have, probably we need to make some f prime or making some g prime from this one. Okay? So if you look this x plus h, if we wanted to make it into the f prime, we need to subtract or minus with f of x, right? So that's the first term, but we still need to have this x plus h that we need to add and minus with something that related to g of x. So that's why the idea to solve this is we need to add and subtract these terms. Okay. If we add those terms or minus those terms, and then we are looking at this h here divided by h, that will be our definition of the derivative, right? So we can make out something from here, and then by looking at this bottom here, it seems that we are on the track, because g, and it seems if this is 0, it's g squared, right? So we are not really doing anything from this one here. It's still just as it is. Okay. What we are going to do is we need to manipulate this numerator, right? So let's just add and subtract the form. So limit let me write fx plus h first and then g of x. Let me write minus first, then plus, so minus fx gx, and then plus fx gx. And then minus, and then g, x plus h, and then write down the same thing, h, gx plus h, g of x. Okay. Now grouping f of x and g of x. So first we can group the g of x here, which is fx plus h minus f of x, and then divide by h, and then minus f of x, g x plus h minus g of x. And then this will be g x plus h and g of x. Okay. So I move out the h to here. And then if you look closely, we know that this will be the f prime, right? This will be f prime. This will be g prime. Okay. My suggestion is if you want to maybe clearly understand what's going on here, you can try doing the same thing from the very beginning without really looking at this. No. And start thinking how we can make it into our proof for the product rule or the quotient rule. And then from here we know that this will be f prime and this will be g prime, right? And then we can write down that the derivative will be g of x, f prime x minus f of x, g prime x, and then divide by g of x, and then this will be squared. But usually I'm suggesting to write down the formula with the terms f at the beginning so this will be the quotient rule. So I'm usually writing f always at the beginning, like the product rule, to make sure that we stick to the same concept, because in quotient rule, the difficult part is if you forget which one is which, right? So always remember that the first thing here, the top equation will be here, that you need to derive. Okay, so we get the basic power rule, which I think everyone familiar with, the product rule, the quotient rule, and the next section. I think we will go to trigonometric first. Okay, trigonometric. Okay, so we will have trigonometric. We have already exponential, also exponential, product rule, quotient rule, and now we can look on the trigonometric. Okay. So we start from the graph of sine. So derivative of trigonometric. Do you think is it too fast or too slow? Or okay? Okay, right. Okay. If you think it's maybe too fast, please let me know. Okay. So f of x is equal sine x. Okay. Okay, sine, as you may know and you are really familiar with, we can develop some value, and in the Cartesian, if we are having some from 0, maybe pi over 2 here, pi, here. Okay, let's say this is our graph of sine. Okay, before we move to look on how the graph looks like and how we can take this graph and then maybe assume or estimate what will be on its derivative from the graph. The sine, if you know or notice, and maybe if you learn biology, you know that in your nose you call that sine, right? You like having some allergy, there's something wrong with your sine. You know why it's called sine in your nose? Because it has a curve. So sine is appear, or the word came out as a curve in terms of bow and arrow. Because it came out from India. In India, when people, they are correlating the curve with some angle, and then they formulate the words sine, and then I think it goes to some other countries, other cultures, and sine called, I think in Latin it's sen, right? Sen, right? And then there are other words aside from sine. It's called a cosine, right? Which means it's just co means complementary of sine. Which means that the sine and cosine, they will always be complementary. You remember the angle, how the triangles looks like, the circle, okay? So if you add, like, the difference between sine and cosine is just a pi over 2, right? The phase difference. If you remember the angle, the quadrant behavior on sine and cosine. Because if this is sine, then your cosine start from here, right? It's practically you shift out pi over 2, the difference. Okay? And now, if we take this and then let me write here, maybe completely like that. If we take this graph and then let's imagine what will happen with the f prime. If we look here, okay, we have slope that is 0, some slope here that is probably a constant, and slope here that is also 0, 0. Okay. With the same techniques and methods that we have learned, I think last week, we can predict that the derivative of this sine, let me draw here, this is 0, so let me just go to write the 0, that this is 0, that is pi over 2, 0 here, that this is 3 over 2 pi, and also 0 here, and also 0 here. So this will be, if we draw, or maybe too high, be going to be here. Okay. And practically we get that this is the cosine, right? So from the visuals, we can actually estimate the sine becomes cosine. But how about if we try to take the sine into our limit definition, into derivative definition with limit? That would be a different case. Okay. Different case, and we need to have some other study as well. Okay. So let's just try and solve the limit. So if we have the first derivative, okay, if we take the limit as h approach 0, so let's change all with sine x. So sine x plus h, and then sine x. Okay. Let's expand sine x plus h. I hope still remember. We have sine alpha plus beta. This will be sine alpha cos beta plus cos alpha sine beta. So this will be equal plus cos x sine h minus sine x divided by h. Let's group sine x together. So limit. So sine x, this will be cos h minus 1 over h, and then plus cos x sine h over h. Okay, let's separate the limit. So the first limit is limit h so let me write all with terms of limit so you can see that the separations. I think we can write also limit here to make it the same with the other one. So we need to prove this and this. Okay, and I think to prove that, I think I will do that on next Tuesday. So I will just stop here. So at least you get the basic of derivative, product rule, the quotient rule, exponential, and introduction to trigonometric. Okay. So I think we can wrap up for today's class. Okay. And next Tuesday we will continue a little bit, and then having some exercise. Okay. Having some exercise on especially chapter 2. Okay, chapter 2. Okay.